Okay, now we have a projectile motion problem. There are also several unknowns here, so we're going to see how we're going to analyze this. So an arrow is shot from a height of 12 meters. You're given the initial height. You're not given the initial angle. You're not given the initial velocity. So you're told that the arrow goes and hits the ground and lands in the ground and gets stuck a distance of 70 meters from the base of the building, and the angle at which the arrow gets stuck in the ground, so you go over there to pick it up, you measure that angle, the angle turns out to be 65 degrees from the ground. Given this information, 70 and 12 meters, and the angle where it's stuck in the ground, how can we find the initial angle of the arrow? How can we find the initial velocity? Once you find those, then you can answer any other question about this problem. You can answer the time that the journey takes. You can answer the maximum height of the arrow or anything else. Okay? So we use the equations of projectile motion. X is equal to v initial cosine theta t. See, we don't know the initial velocity, we don't know the angle, so we're not going to know the cosine, and we don't know time either. So we have basically three unknowns here. V initial cosine theta t. And then we have the y equation. Y final is equal to y initial plus v initial sine theta t minus 4.9 t squared. Y final we know is 0. Y initial is going to be 12. Again, we don't know v initial. We don't know t. For this one, do we know x? Yeah, that's 70, right? So we have 70 is equal to v initial cos theta t. So far we have two equations. The x equation, the y equation, but we have three unknowns. V initial, t, and theta. So somehow we have to use this knowledge of the 65. What does that mean? Well, the angle at which the arrow is stuck is related to the angle of the velocity that it was going at, right? When the arrow was going, it had a certain final velocity, right? The angle of that velocity was 65, below the horizontal, right? This angle and this angle are the same. So the angle that you get stuck when you hit the ground or when you hit the wall is the same as the angle that you were going at. Except that the angle that you were going at is possible that it's negative because it's headed downhill, right? It's headed downward. So the angle that the arrow was going at must have been negative 65, right? That's why it got stuck at 65. So what we're going to do is we're going to analyze the final velocity, V final. This is Vx. This is V final y. We know that the x component of the velocity, if you ignore air friction, does not change. The final component of the velocity, the y component, does change. This angle is negative 65. That's the information we're given, right? The reason I say it's negative is because you need the negative to specify the fact that it was going downwards, right? So what are we going to do? We're going to say tangent of negative 65. Tangent of negative 65 is what? V final y over Vx. Okay? And so from there we get tangent of negative 65 is equal to negative tangent 65, right? Because tangent is an odd function. What's V final y? It's V initial y minus 9.8 t. That's the first equation of projectile motion. The initial component of the y, the initial y component, minus 9.8 t, and then this is Vx is just equal to V initial x. The x component of the velocity doesn't change. So from there we have what? Negative tangent 65. V initial y is what? V initial sine theta minus 9.8 t over V initial cosine theta. Okay? So this is the x component cosine, this is the y component sine. So Now we can actually find a way of putting all three of these equations together, this one, and this one, and solving for the variables. Let's do this. Let's divide this by this, and then this by this, and then let's take the negative and switch the order. Okay, so we're going to get tangent of 65 degrees. Switch the order of this, and you get 9.8t over v initial cosine theta, right? And then this one will come next, minus v initial sine theta over v initial cosine theta is going to be what? The v initials are going to cancel. Sine over cosine is going to give you tangent. Okay, tangent theta. Okay, now what we have? We basically have three equations here. Let's call this equation 1, equation 2, and equation 3. How can we combine this so that we have basically one equation with just one unknown? What's the easiest way? Well, you could try various combinations here so that algebraically works out the nicest and the easiest. One of the best ways is to approach it from this point of view. First of all, you recognize here that v initial cosine theta is equal to 70 over t, right? V initial cos theta is 70 over t. One of the first things we can do is substitute that into here. And then what we do is we get this expression. We get tangent of 65 is equal to 9.8t over, and then v initial cosine theta will become 70 over t minus tangent theta. So you have tangent 65 is equal to 9.8 over 70 t squared minus tangent theta. So later on we can use this equation, we can utilize it somehow. We have a relation between t and tangent theta. The other thing I'm going to do is I'm going to take v initial and then write it as 70 over t cosine theta. Take the cosine theta and bring it down here, and then substitute this into this v initial. So you have 0 is equal to 12 plus, and then where you see the v initial, put 70 over t cos theta, and then you have sine theta t, right? So I substitute that from here. Then minus 4.9 t squared. So where does that get me? So I have 0 is equal to 12 plus, you have 70, and then the t cancels the t. So the t is gone. And then you have 70 tangent theta. Right? Sine over cosine. Minus 4.9 t squared. Okay. Well, actually, if you look at this, this gives us a clue as to what to do next. We have an expression here for tangent theta, and then we have an expression here for tangent theta, right? So we can take this, solve for tangent theta. Say tangent of theta is equal to 9.8 t squared over 70 minus tangent of 65. Right, take that over here, bring the tangent 65 over here. Take that and substitute it into this tangent theta. So you have 0 is equal to 12 plus 70. And then tangent theta will be 9.8 t squared over 70 minus tangent 65 minus 4.9 t squared. Now I can distribute the 70, and I only have one unknown in this equation, and that's the t. You see? Twelve plus 70 cancels that one. 9.8 t squared minus 70 tangent of 65 minus 4.9 t squared. So it actually ends up not even being a quadratic equation. It's just t squared and some numbers, right? So this 70 tangent 65 comes over here. 70 tangent 65 minus, and then 12 equals, so 70 tangent 65 minus 12 equals 9.8 minus 4.9 is 4.9 t squared. We take the 4.9, we bring it here, and then we can take the square root of that, right? 309. So that means this trip took 5.309 seconds. Now ultimately we weren't even asking that, but that's the first variable that we found. Then we can take that and we can put it into here, we can find out what angle the arrow was shot at. Tangent of theta is equal to 9.8 over 70. That number 5.309 squared minus tangent of 65. And then you can solve for the angle, okay, was shot at. Right? So theta is going to be tangent inverse of 1.801 60.965 degrees. All right, so it was shot at 60.965 degrees. And what was the initial velocity? Now you can put it all in and you can find out the initial velocity. So V initial is equal to 70 over the time here. So that would be 5.309 times cosine of 60.965 degrees. 7 meters per second. Okay? So now we know the initial velocity was shot at, the initial angle, and the time is 5.309. Does the angle make sense? Let's see. If it's shot from a height of 12 meters at 60.965, does it make sense that it goes and it comes back and it lands and it gets stuck at 65? Does it make sense that this angle is larger than that? The answer is, oh yes, definitely makes sense. Because when the angle goes up, when the arrow goes up, the angle gets less and less and less and less. When the arrow is on the top of its path, the angle is 0. And as it comes back, when it comes back to the same height, this angle should be what? Negative 60.965 degrees, right? When it comes to the same height that you shot it at, it has the same angle going down that you shot it, but it's negative. And then when you keep letting it go down, 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 it perfectly makes sense that by the time it hits the ground, it's negative 65. So it's about 4 degrees larger than the angle that you shot at, because this height was not very large. It was only 12 meters, right? So this angle shouldn't be that much larger than that angle, okay? So the answer makes sense, and this is a really good example of there's 3 unknowns in this projectile motion problem, but yet we have 3 equations and we can combine them together and solve for those unknowns. Thank you very much.